Hi, this is Paul from Foresight Tech. In this video, I will introduce a half-life decay model, which is an exponential decay model and widely used to describe the mass of a radioactive chemical element. The nucleus of a radioactive element is unstable, so the mass will decay because of radiation. The mass decays according to a half-life decay model. The most famous application is the modern technology of carbon dating, which we use to predict the age of a fossil, right? The foundation of this technology is carbon-14 decay model. Here is the half-life decay model. Pt equals P0 times 0.5 raised to the power. See, the parameter no longer are decay rate, right? Which is T 1/2. This is the most important parameter. We call it half-life. Okay, and if the model describes the mass of a chemical, so Pt is the future value, or you can call the remaining mass of the chemical, right? P0 is the initial value or the initial mass. T is the time passed, so T half, okay, is the half-life. Let me draw a graph to show you the definition of the half-life. Let's draw a Cartesian system first. Let me put here. Okay, so if this is the time t, right, and the y coordinate, let's put here, and which is the origin here. So this is the mass or the future value. Now let me put the beginning. Suppose the initial mass or initial value P0 here, and then what is T1 half-life? Half-life means the time, okay, go through the half-life, the value or the mass go down to half, which is here. That's 1/2 times P0, right? How long? Let me put the time here. Okay, so let me highlight from the initial time to this point, and the value goes down to half, which means we have a point. You see, this is the real point at the time, the first time. Let me define it. This is 1/2, which is the half-life. Okay. Now, if I give you another point, if we go through another half-life, so the time goes to 2 times the half-life. You know, by the definition, go through half-life, the value go down to half. Therefore, this time go down to half of a half, which is a quarter of P0, right? Okay, let me get this point. Now we do have a data point here. The same, if the timer go through another half-life, which is now goes to 3 times 1/2. Of course, the point goes to this high. It's very low. Now, how low? Half of a quarter, right? This point, which is 1/8 times P0. Makes sense? If it goes on, we will go to 1/16 times P0. Okay, if I link all these points together, see, from the beginning goes down, decay goes down to here, goes down to here, goes down to here, goes down, and if the time goes up into infinity, and the value will definitely goes to 0, go down to 0. And this is the curve for the half-life decay model, or you know, is exponential decay, right? Let me put one more. If I put the beginning, I say remain 100%. If some of you use this, and then go down to the second should be 50% of the mass left, right? If we look at how many percentage left, and goes down to 1 out of 4, a quarter, which is half of 50%, that's 25%. Okay, so half of 55%, which is 12.5%, goes down on. Okay, so that's the definition. Let me draw another graph. Okay, will show you the same meaning as this graph shows. So go from the beginning, which is P0, right? That's the initial mass, initial value, let's say. Okay, go down to half, which is P0 over 2. How long it need? It need a half-life time. That's the definition, right? Go through half-life time, the value goes down to half. Okay, so let's go on. If we go through another half-life time, you know the value goes down from here to P0 over 4, right? Continue if it goes on another half-life of the time. And the value now from here goes down to P0 over 8. Continue, goes on. Okay, the same. If we look at the percentage, at the beginning is 100% left. The second is 50%, right? Goes on 25% and 12.5%, and it goes on. Okay, so that's the definition for the half-life definition. And this curve, let me highlight the formula. Okay, which is this. That's the model of a half-life decay. And at the end of this video, I will verify this formula. And we also were going to find the relationship between this half-life decay model and the original exponential decay model. Okay, but first, we have to practice this formula. Here is the first question. Carbon-14 decays exponentially. Do you remember? I introduced at the beginning. Carbon-14 is a radioactive chemical, right? And it decays by radiation. The carbon-14 decay model is the foundation of carbon dating, so it's important. Now we know the half-life is 5,730 years. If there are 40 grams present now, how much will be left after T years? Find the half-life decay model. Of course, what we need is the half-life decay model formula, right? Let me copy the formula. So I put here, which is PT, the remaining mass at the time T, or the future value, equals P0 is the initial times 0.5 raised to the power of T over T 1/2. Okay, that's the formula we need. Let me highlight. All we need is this formula. Now, what do we need to do? We need to find what is P0 and what is T 1/2, right? So to put the model. So P0 initial, can we find 40 grams that at the beginning? So this is a initial P0. Therefore, we know P0. What is T 1/2? It already shows us. This is the half-life. So we do have this. Therefore, we do have the formula right now. Plug into the formula. See, we have PT equals P0 is 40 grams. Okay, but here times 0.5 raised to power of T over initial value. Half-life, which is 5,730 years. Okay, and this is the model already. Describe the value at the time T. okay, of carbon 14. Let's practice another question. Here is the second question. Lead-209 is a radioactive isotope. It has a half-life of 3.3 hours. We know it decays very fast, right? Suppose that 20 milligrams of this isotope is created in an experiment. How much will be left after T hours? Of course, we need to find the half-life decay model. What do? We need to look at the formula. Okay, let's copy it again. So Pt, the future value, equals P0 initial times 0.5 raised to power of T over T half. Okay, again, let me highlight. That's the one we need. Okay. Now we plug P0 and T1 half. What is P0? Initial value, it says 20 milligram. And put here, that's P0. So we know P0. What is half-life? It says 3.3 hours. We already know. Let me put here, T1 half. So we also know this. And plug into the formula. And we will build the model, okay, for future mass or future value PT. What is P0? 20, right? 0.5 is the base raised to a power of T is the variable. So T1 half, we know 3.3 hours. See, that's the model we need. Now, let's verify the formula. Here is the half-life decay model. Let's verify this model at 3 time points. Okay, 1 half-life time, 2 half-life time, and 3 half-life time to see if the remaining value Pt is the same as we expected. Let's plug into the first time point, okay, which is T equals 1 half-life. Okay, I put half-life T1 half. What is the value of Pt now? Okay, so Pt equals P0 times 0.5 raised to now. What is T? T is 1 half-life time, right? And then over T1 half. Now you know. So we can cancel this and this. That's 1. Okay, the power is 1. So we have P0 times 0.5 raised to the power of 1. What do we get? We get 1 half times P0. Yeah, this is what we expected, right? And the time goes through half-life. The value goes down to half of the original, which is 1 half times P0. That's good. Now we verify the second time point, which is T equals 2 doubling time 2 times T1 half. See, what is the value of Pt? Okay, so we plug in. So P0 0.5 raised to now. Okay, the denominators, they are the same. What is the numerator T? T is 2 half-life. The same, we're going to cancel this. So what is the power now? The power is 2, right? So we have P0 times 0.5 raised to the power of 2. Of course, to calculation, what do we get? We get a quarter times P0. See, that's true. Why? Because it goes through another half-life and the value goes down to half again. Half of half is a quarter. 1 out of 4, this is true. The last, let's go to T equals 3 half-life time, okay, which is this. We going to Find out what is the PT. The PT equals P0 times 0.5 raised to a power. Now see, the denominator is the same. What is the numerator? We plug 3 times half-life in. You know, cancel this. We get the power is 3. Therefore, equals P0 times 0.5 raised to the power of 3. Do calculation. That's exactly is 1/8 times P0. Is this true? Yes. That's what we expect. Go through another half, goes down 1/2. 1/2 of 1 out of 4, which is 1 out of 8. So that's true, right? Okay, so this is the verification. Now, let's find the relationship between this new exponential model to the old exponential decay model. Here, the first is exponential model we learned before, right? If R is less than 0, okay, we call decay rate, right? So it's an exponential decay model. The second one is a half-life decay model. We are learning in this topic right now, which is also an exponential decay model, right? Both are exponential decay models, so we should find a relation between them. Now let's do a little math to find out the relation between R, which is decay rate, and T1/2, which is a half-life. Let's start from the old one. PT equals P0 times 1 plus R raised to the power T. Okay, and I will finally convert the old model to the new model. Okay, and first, let me convert this old base to the new base 0.5, which is this P0 times the new base 0.5. Okay, now I have to raise to this power log 0.5 at 1.R. See, that's a big one. Okay, if I highlight, this big one is just equals the old base 1 plus R. Therefore, I have to put a big parenthesis. Okay, raised to the power of T. Why I can do this is called change base. We do have a rule in algebra. We call the inverse rule. Let me show the inverse rule here. Inverse rule, okay, which we use to this step. That's A raised to log A x equals x. Okay, see, if we set A equals 0.5 and the x equals 1 plus R, therefore exactly this is true. That's the first step. Now we can continue. I go to the second step now. Okay, we look at this 0.5 raised to a power. This is a number, and then raised to another power. Power of power. Do you remember? We do have a power rule of exponent, right? So we can get this result, which is P0, the base 0.5. Now the new power is times the two powers together, which is T times log 0.5 at 1 plus R. Okay, so this we call power rule. Let me stay up here. It's power rule we used for this one. That's A raised to a power m. If we raise to another power again, the result is just times the two powers together to get the new power. Okay, so almost the last step, because the base is 0.5 and the residual power, right? See, the new model is almost the same, so let's convert this one directly to the new model, which means this one t over t at 1/2. Okay, so what do we need? Let me get this color. We need this power equals this power, right? If these two power are the same, therefore we definitely convert from the old model to the new model. Therefore, we have this relation. Okay, let's put here. Now we do have the two power are the same, which is t times log 0.5 at 1 plus r equals t over t 1/2, right? Okay, so this is the equation. We can find the relation between r and the t 1/2. Let's simplify. See, both has t, right? So we can divide it by t to the left, divide it by t to the right. Now we get the result, which is this. So a flip, let's flip both sides. Therefore, I get a t 1/2 half-life equals 1 over log 0.5 at 1 plus r. See, that's the relation we finally got. Okay, so I may highlight this one. That's the result. Which means if we know one, we can definitely find the other, right? If we know decay rate, we can find the half-life. If we know half-life, we can find the decay rate using this formula. Okay, so that's all. Thank you.